So it leads us into how do we prepare the surfaces? And so how do we see these grain structures? Because if you were to just look at a cut metal surface, you would have no way to know what's going on underneath. And so what we take advantage of is the performance of these. So we need to make the sample flat, and we do that through a series of grinding and polishing steps. And so as metallurgists and material scientists, we work real hard to try to get a sample flat. So we'll go and polish it almost to a mirror-like finish. And so it's very highly reflective. So if I would put it onto the microscope, I would only see light being reflected off there. I wouldn't see anything. So I need to have some surface topography to give me some type of contrast in the microscope. And the way I do that is by etching the surface. And by etching, what I mean is that I literally take an acid, and the acid will react with the different crystal orientations, especially in a polycrystalline material, in different ways. So going back to that lead ingot that we had seen earlier, we see that each of the grains has a different contrast to it because of the different grain orientation or crystallographic orientation, even though they're all the same crystal structure. And so what it is, this is what the etching refers to. And so we can reveal these grain boundaries very closely as well. This is an iron chrome alloy, which is basically a ferritic stainless steel. It's all BCC, but what we tend to see is we have these grains that form. And if we think about it, we're etching the grain boundaries. So what we end up with is this difference in surface topography. In this case, the black tells us that there's no light reflecting out of it. We see the light images before coming off the grains themselves, but the grain boundaries tend not to have reflected light back into the microscope. So we're really producing almost grooves at these grain boundaries. And it gives us that etched surface that allows us to be able to characterize that material. So once again, optical microscopes, scanning electron microscopes, typically where we're going to operate in terms of structural materials. You'll see some transmission electron microscopes, but outside of a research environment, it's rare that you're going to run into TEMs. But working in, whether you're working in a factory, whether you're working manufacturing, anything like that, you will see optical and scanning electron microscopes consistently used to try to understand what's going on or how failures might be occurring in your material. Even the naked eye is of use. I like to think in terms of inspecting welds. A certified welding inspector is an actual title. It's governed by what's called the American Welding Society. And one of the tests that a certified welding inspector has to go through is an eye test, because they will look at weldments and be able to determine if there's any cracking in that weldment. And a lot of times they use their naked eye. They use what we call an eye loop, which is basically a 10x magnifying glass. And they'll be able to see some of these resolutions. And they're more in the millimeter, sub-millimeter range. Optical microscopes and scanning electron microscopes tend to put us into that micron range that we might be interested in for different crystal structures. So thinking just in terms of these grains, how do we measure them? Because if we just look at a series of grains and we don't have a set of standards put in place, how do we determine what the grain size is, and how can we repeat that so that we can obtain similar properties each and every time? So we can define grains or specify them typically in diameter and area. I've not seen a lot of, you can use grain volume, but not as useful as what you may get from looking at the size of the grains. We look at them in terms of diameter. And the one primary way to obtain this is what's called the linear intercept method. So in this case, what the image shows are we have straight lines drawn across the micrograph. And you will look at several micrographs in adjacent areas and try to obtain some statistics on this. But you count the number of grains that are intercepted. So every time you run into a grain boundary, you count it. And then the length of the line is divided by the number of times that the grain boundary intersects that line. And that gives you the average grain diameter that you would have, or the grain length or grain size. Now, that tends to give you something in microns. From a materials perspective, that is usually acceptable. I'd like to know what the grain size is in that type of just length measurement. Now, ASTM has come up with a different way of doing it. It's relatively simple, it's convenient. So they take an average grain size and they assign it a number between 1 and 10. And because it's a standard, we have to have as you would expect, some level of standardization to how these micrographs are taken. So the requirements within the ASTM standard are that they're all taken at 100x. And if we're going to specify steels, it's widely used in steels. So we express it as a grain size number. And within that grain size number, we can look at it two different ways. We can directly measure it, or we can use a comparison procedure. Now, the comparison procedure is widely used. I am not going to have you use the comparison procedure, though, because there are certain plates within the ASTM standard. Allows you to go in, know what your base magnification is, and just compare what you see to these plates or examples that are provided within the specification. And you can get an idea from that, basically, of what that corresponding grain size number are. So you just basically can put these, say, on a transparency of some type, overlay it onto the micrographs that you may have, and determine whether you have a grain size number. That's not always feasible, though, because you see here you have a limited number of materials that you may be looking at, the plates which would correspond to those, and how you would go about it. Now, what we can see, though, is that you can correlate the grain size, usually measured through a linear intercept method, and a grain number. And we can use this equation here, this capital N equals 2 to the lowercase n minus 1, where that lowercase n is the grain size number, and then the n is the average number of grains per square inch. So these can be measured, and you can determine that grain size number just using this and a series of measurements. Now, once again, the important issue here is the average number of grains per square inch at 100x. I would highlight the 100x because that's part of where the standard tends to reside. And so we can calculate that. Let's say we measure 45 grains per square inch at a magnification of 100x. And so we can do the algebra, go and convert that number of grains we measured, and we can come up with a number of 6.5 for that number of grains we can measure. So we're not really looking at it and saying microns equals a certain grain size number. What we're looking at is how many grains are there located in this certain area on the micrographs that we're looking at. And so with that, there's a couple things. As we had said before, grain size numbers are between 1 and 10. If you calculate a grain size number in this way and it's not between 1 and 10, you need to go back and look at it and redo it again because it cannot be outside those number ranges. So what if the case comes that the 100x doesn't give you enough grains, or they're too small to see? In this case, we're going to say it doesn't give you sort of enough grains. You don't have a good feeling that you have enough statistics to do it. So you go and you broaden out. Your grain size is a little bigger. It's a little bigger than you would like. So you go to another type of magnification, or you go to a lower magnification. Now, you still measure a number of grains, but you need to take into account what that magnification is. And what you can do is normalize it to the 100x. And so that allows it to maintain the standard. So if you have a magnification other than 100x, you need to use this equation. And we can see how if we have a certain grain size number at a magnification of 85x, we see how many more grains we counted. In this case, we were only at 45 grains. In this case, we're counting 60, almost 63. That's key, is statistics. It's counting enough grains to feel comfortable that you're capturing what that grain size is, or that average grain size. So let's say we have another metal specimen and we've gone to a magnification of 75x and we counted 45 grains. The ASTM grain size number in this case comes out to about 5.7 if we calculate it. So we can get an idea just off these of what these ASTM grain size numbers are. Now, I recommend that you run through the couple practice problems. Just make sure as you're looking at the ASTM grain size number that you take into account what the magnification is. So if you're going to get tripped up on an exam or anything, it's not taking into account a different magnification from 100x when applying it. So it's a rather quick lecture, but I think it hit upon the main points that I wanted to capture, is to give you some little bit of background so you have a little bit of knowledge going into how do we characterize these crystalline defects and what are our common characterization tools that we use. And we see that you're, for the most part, going to be running into scanning electron microscopy and optical microscopy. And then knowing that grains are a primary means of determining strength or properties of materials, we went over how to use the ASTM grain size number determination to allow us to calculate these and then be able to understand what that actually means when we see certification materials. So this completes our lesson 2 lectures. So make sure that you do all of the assigned problems, submit those onto the website, and then we will come back and meet again for the beginning of lesson 3.